Hey folks, I'm Mr. Rose, and if you don't know that, that's a problem because today is the last day before the MCAS, and I'm going to try and finish up our heat notes. So get ready for some awesome sound effects. The last thing we spoke about where there were three types of, uh, sorry, not three types, three ways to heat objects or to have heat transfer to objects, and those ways were conduction, convection, and radiation. Conduction was literally increasing internal kinetic energy of an object through contact. We can't always see that, but sometimes things get so hot you can see them. They glow like red or white hot. Like, I don't know, look at that, a light bulb. Here we go, see the light bulbs. The second way is convection. That's putting the entire fluid in motion. So if you look at my little screen, that's like hot air rising to the top, then getting pushed to that side, then cold air falling, and that convection current. And then the last part is radiation, which is transferring heat through electromagnetic waves like infrared radiation. So let's see if we can figure out what type of heat transfer is involved with these three types of things. Heating a room with a fireplace. Well, heating a room with a fireplace could do a couple of different things, but generally heating a room with a fireplace is going to be heating through electromagnetic radiation. One way I like to say it is like when I'm standing in front of a hot fireplace, feeling the warmth. It heats me up through infrared radiation without necessarily heating up the air around me through electromagnetic waves. So sometimes I just think radiation is heating an object without heating the surroundings. That's not the best definition, but it's a good way to think about it. What about cooking an egg on a frying pan? Well, if the egg is touching the frying pan, that would be conduction, because I'm literally heating the egg and raising the internal kinetic energy of that egg. The last is, what about the roof of a house becoming hot? Well, that's going to be kind of hot from the sun, so that again would be heating by radiation. Now, heat, remember, is energy, which means heat can do things. In other words, it transfers energy. Heat is usually the end product, right? We lose things, like when we lose energy, we lose the heat, sound, and friction. We often take that as a waste, but there's this concept called a heat engine, which is like making something happen. So look through this if you'd like. Send me an email if you want to ask me a question, but this is just some extra information. Heat engine concept. Again, you have these notes. Go back and look through the PowerPoint if you'd like, but moving forward on what exactly heat is. Now, heat brought to us by the letter Q, we know, but I want to be sure that heat can do work. The reason why I'm making a big deal about this, as you read some of these notes, is I'm going to say over and over again, heat and temperature are very, very different things. So while heat can do work, that's because it transfers energy. So like air over a hot car, it's lofted. That's gaining kinetic energy because the molecules are getting faster. When we see red lights, when we see the filament glowing in a light bulb, that is physically doing work because I can see energy transfer. So heat can do work and radiate energy. So recall energy. What exactly energy? Energy was the ability to do work, and we just said that heat can actually do work. Now, this is what I was just talking about. Heat and temperature are very, very different things. What do I mean by that? Heat, we know, is a form of energy, which means heat is measured in joules. Temperature is literally nothing. It is a scale. It is a man-made scale. You probably know at least two different temperature scales, Celsius and Fahrenheit. There's a third one that's Kelvin. In physics, we're going to use Celsius. It is literally just a measurement system. The temperature of something indicates how much kinetic energy those objects have. In other words, it's measuring how fast the molecules are moving. Heat is energy, which means energy can do work. Heat can do work. Temperature is not energy, which means it can't do anything. For lack of a better example, the temperature scale is like a distance scale. If I want to know how far away something is, I can use a meter, I can use an inch, I can use a mile, I can use a kilometer, but that's just a scale. It can't do anything, right? So the temperature scale reflects something, reflects the amount of energy, just like the meter scale reflects a distance. So temperature is these things, or what temperature is. Temperature is the measurement of a total amount of energy. Temperature is the measurement of the total amount of thermal energy in an object. Temperature is a measurement of how much heat something can give off. Temperature is a measurement of how fast those molecules are moving. Notice every time I had to include that measurement of, while heat is actually those things. Heat is the actual energy that is absorbed or given off of an object. Heat is actually the motion of the molecules. It shouldn't say a measure there. Heat is actually the motion of the molecules in the object. Heat is the total amount of molecular energy. Heat is energy. So, very, very, very simply, every object contains some kind of energy. In other words, every object radiates some kind of energy, usually in the infrared spectrum. The temperature that we record off that thermometer is a reflection of that energy. Temperature does not measure heat. Temperature is measured in degrees Celsius in physics. Heat is measured in joules in physics. The calorie I have here, just because we used it way early in the year, calorie is also a unit for energy. We again are going to use joules, but we use calories like food calories. When we did the stair lab, the power lab, we used calories, like how many calories are we burning? But I just wanted you to be aware of it. In physics, generally we're going to continue to use the joule. So I'm just beating the dead horse here. Joules are energy. The things that represent, in other words, the way that we know how much energy or heat something can either absorb or release, has to do with how big the object is, right? Like if I have a small little baseball, or I had a giant ball, well, the small ball that has a small mass would not be able to hold as much energy as, say, a giant ball. So things that relate to how much energy or heat something can either absorb or relate, one of those things should obviously be mass. Now, what is the baseball made out of? We know the baseball is an insulator. So is it easy to heat up? Probably not so much. That's what becomes with the specific heat. This is a track baton. I'm just grabbing things around my apartment. This is a track baton, and the track baton is made out of metal. Metal we know is a conductor. This has a lower specific heat because this is easy to heat up. So what exactly is specific heat? The specific heat is the ability of an object to either absorb or to release heat. In other words, how easy it is for that object to heat up or to cool down. Different substances, insulators, conductors, absorb or release heat at different rates. The greater the mass the object is, the more heat it can have, the higher the specific heat, the more heat or energy it can hold, but also the harder it is to hold that heat. Finally, we put all this stuff together in an equation. That equation we find on the MCAS sheet is Q equals MC delta T. Now, what do all these things stand for? You can look at the MCAS sheet, but Q stands for heat. I don't know why Q stands for heat. If you're quiet, there's nothing. I have nothing. No, that's just a COVID joke, I guess. I don't know. Q stands for heat, measured in joules. M, we know, stands for mass. This C is the specific heat. Now, every object has its own specific heat measurement, and the delta T is a change in temperature. So remember, the change in temperature right there, this change in temperature reflects how much heat is either given off or absorbed. If the change in temperature is positive, that means it's absorbing heat. If the change in temperature is negative, that means it's releasing heat. And we always calculate that change, final minus initial. Now, we're not done yet. We have to talk about phase changes. So this is the picture I want to look up. Now, when objects change phase, that means they are either absorbing or releasing heat. Or absorbing or releasing energy. In my opinion, the easiest way to understand this is think about an ice cube. If I take an ice cube and I hold that in my hand, well, we know, and here's a review, we know that energy always travels from hot to cold. It will always travel in that direction. So if I take an ice cube and I hold that ice cube in my hand, well, I'm producing heat. about 98 degrees Fahrenheit is my body temperature. My hand is about 95 degrees. So as I hold that ice cube, I'm melting the ice cube. So what's going on? I'm transferring my heat to the ice cube. So energy is flowing from my hand into the ice cube, melting it, which means energy is being absorbed into, so it goes from frozen water or ice into liquid water. Now, if the water is dripping into a pot and then I put the pot on the stove and I boil the water, well, obviously the fire is hot. That is absorbing more energy, so the water absorbs more energy and eventually evaporates into steam. So that whole thing is absorbing energy. We also should know that solids, ice, have less energy than gas or water vapor because that's a gas. The molecules are tightly packed in the solid. They're flying all over the place in the gas. The opposite way for me is harder to keep in my mind. When things start as water vapor and they condense or condensation into liquid water. Well, when have you ever seen that before? Well, let's pretend this is full of, oh wait, this is easier. Pretend my daughter's cup is a nice cold drink on a hot day. Well, if this is nice and cold, well, energy is going to flow from hot to cold, from the air into the liquid to try and warm up the liquid. Well, when that happens, water vapor around the glass starts to cool down, and all of a sudden you make water. There's condensation that ends on the glass. So we are literally, the water vapor is losing energy, going from water vapor into water. And then if I took that water and I put it in the freezer, again, it is releasing energy such that it's becoming solid. It is a release of energy. So it is always absorbing energy when I go from a solid to a gas, or releasing energy when it goes from a gas all the way down to a solid. That is changing phase and energy releasing. So I'd like you to just kind of read through these. This is reviewing everything I just said. Give it a pause, read through. Now freezing is the same thing. It's changing phase. We go from liquid to solid. That's losing energy. Again, give this a pause, read through. If there are questions, by all means, send me an email. There is this special thing called sublimation. This is just extra information. We don't actually need to know this for the MCAS, but you've all possibly seen dry ice, whether it was in a movie, in real life, or in some like demonstration where dry ice is literally frozen liquid nitrogen. But the frozen liquid nitrogen goes right to a gas at room temperature. So it goes from a solid, skips over the liquid right to a gas, and a huge, is it absorption or release of energy? Goes from solid to gas. That is a huge absorption of energy because the gas is crazy and super excited. Now, this is a heating curve, and this is for water. And I want to point out a couple of things. We know that at 0 degrees Celsius, water freezes. So anything colder than 0 degrees Celsius, we have just cold ice. Colder ice, colder ice, colder ice. And this right here, we can calculate Q equals MC delta T. Now, we're going to do a couple of examples on a different video of that exact equation. But what happens to the water when it gets to 0 degrees? Well, here it says that water and ice both exist. This is called hidden heat. In other words, I need to add energy all the way. Look at this, heat added in, well, they have it in kilocalories, but we know it could also be in joules. We're adding heat into this water. So as we're melting that ice, so this hidden heat here is not actually increasing the temperature of the water, but it is absorbing, absorbing, absorbing. So you actually have two different things here. You have water and ice that can exist at 0 degrees Celsius, which is another example of how temperature is not energy. We need to add energy to that ice, and we can have literally water at 0 degrees. Then all of liquid water, here's this Q equals MC delta T, and I know that because, look, I can measure a difference in temperature anywhere on this curve. So if I knew the mass of the water and the specific heat of water, which is 4.186 joules per gram times degree Celsius, I can figure out how much heat or energy it takes to make water get up to 100 degrees or start to boil. Now, what you might not know is all here. Look at all this energy that has to be added. This is called, again, latent heat. It is hidden energy. It takes energy to change phases. So all of this energy is when the water is boiling. So I'm adding more energy, more energy, more energy, more energy. No matter what you do, water, liquid water that is, cannot be more than 100 degrees Fahrenheit or 212 degrees 212 degrees Celsius, or I did it again. Water cannot be hotter than 100 degrees Celsius or 212 degrees Fahrenheit. That's when water is boiling. And when water boils, eventually, after I add all of that, look at that, I add all of this energy, 740 kilocalories, those are food calories basically, of energy, I finally get the water to be steam. So the water can be 100 degrees Celsius, and then steam, look, steam can be way hot. We can have superheated steam, and steam also as a gas has a lot more energy than the boiling water, and you can see that. The energy of the steam is way higher by comparison to the water, which is also why you can burn yourself worse with steam than with water. That is pretty much everything that I have to tell you about heat transfer. Hopefully you'll watch the next video, which will have a couple of examples, and knock them dead on the MCAS. See you folks sometime this week. Good luck. Email with any questions or concerns.